Good afternoon, everyone. I hope you are doing all right. So, we were talking about physical optics and we talked about interference and diffraction. So, in physical optics, we consider light as a wave and we look at the situation when they, pass through very small opening. And it turns out that when light reflects rather than just passing, rather, when it reflects from very thin films of, for example, oil or soap, what happens? It goes through the interference. So today we're going to be talking about that. So since we're talking about interference on thin film, we have to know, you know, we have two kinds of interference, constructive and destructive. We already talked about. And what's the condition for that? So this constructive and destructive interference can be thought as in terms of, let's say, change in phase or in terms of change in path. Change in phase or change in path. So in this case, what we see is change in phase is 2 pi radians, which is equivalent to 360 degree. And why is that? Because it starts oscillating from here, let's say, goes opposite and comes back to the same position. So that is one complete oscillation. So it's like a one complete rotation. Okay, we can think of something like that. And because of that, we have this 2 pi radian phase difference here. And in terms of path difference, we can talk in terms of wavelength. So when there is one complete oscillation, we say, okay, it is one wavelength complete. So in that case, what happens? The path difference is exactly one wavelength. So one wavelength and 2 pi radians, they are not equal, but they are equivalent for the constructive or destructive interference. Okay, so in this case, this condition when the phase difference is equal to exactly 2 pi or path difference is exactly equal to one wavelength of the light, in that case, what happens? This wave interfere with each other and that interference is constructive. So that means they reinforce each other and produce bit brighter spot. When in terms of, like when we talk about light, if we're talking about sound wave, then that produces little louder one, right? So why is that? Because when they are in phase, if we are talking about two waves, for example, their, let's say, top here crest and crest matches, so they reinforce each other, giving us double amplitude, and the intensity is directly proportional to the amplitude square. So when amplitude doubles, intensity becomes 4 times larger. So because of that, it appears brighter. Okay, so the equation for that condition is this. And in terms of thin film, what happens is we're going to be talking about path difference as well. So if the thickness of the film from which it is, let's say, reflecting and combining with the previously reflected wave, we will talk about that. Then in that case, what happens is we're going to get constructive interference when thickness of those thin films match as the integer multiple of this wavelength. Okay, so m, they are numbers. M could be 0, could be 1, 2, and so on, right? And of course could be -1, -2, etc. as well. So that is the condition for constructive interference. And destructive interference, basically when they shift a little bit. So for example, pick up this one is here, that is matching with the trough of the other one. So they have this canceling effect because of that, and they go through this destructive interference. And when does that happen? When, see, in terms of phase, the phase difference between the peak and the trough is exactly equal to pi radian because it's half cycle, or in terms of wavelength, it is half of the wavelength. So because of that, what happens is we can write that something like, okay, so constructive was this, and you shift that by half cycle. So phase really, equivalent to half cycle is pi. So when you do that, you get this destructive interference conditions. Okay. And same thing goes with the path difference as well. So this is basically a review of what we had already learned. And since we're going to be using this idea, so if you forgot that, and if you don't keep this in mind, what we're going to be talking may not make much sense. Okay. So those are, constructive and destructive. So when light enters to a thin film like this, so light can reflect from right there or may go all the way here and then reflect from there. So there is transmission going on, there is reflection going on, and what happens is when wave gets reflected from a boundary, what happens? It goes through phase change. So for example, here what do we see is there is this wave in a string, okay? So it is now, see the peak is on this side, and this one is a fixed boundary, so that means this cannot wiggle around. So when it reflects from the fixed boundary, then what happens is phase becomes exactly opposite. So here this V is showing this is moving in this direction to the right on the screen, and the V over here indicates it's now moving to the left. So this wave, when it was coming to the boundary, and then this wave is when it's already reflected. So when it's reflected, what we see is there is 180-degree change. So when it is trough, so for example, here there is peak or crest, and there is a valley or trough. So that means they have this opposite phase, we say, and in terms of number, it's 180-degree or pi radians, right? So in terms of light, what happens is, what is fixed boundary for the light? So for example, if we have light coming from low refractive index to higher refractive index, right? So lower to higher N here means refractive index. So for example, air has a refractive index of 1, and for example, water has a refractive index of, let's see, around 1.3. So that means when light comes to the boundary of water, for example, light coming from the sun, when it hits the swimming pool, for example, or river bed, I mean, the top portion of that river or the water on the river or on the ocean, what happens? It gets reflected, and that boundary acts like fixed boundary because it has higher refractive index. So water, air, for example, okay? So higher refractive index of water means it acts like a fixed boundary. So that means when the wave reflects from the water, what happens? It reverses the phase. It changes phase by 180-degree. Okay, so that's what that is. And now, however, if we have a loose boundary, so in this case there is this ring, so this is still a string, but there is a ring now. That ring can move up and down, okay? So that means it's a loose. So in that case, what happens is the reflected wave has the same phase, so there is no phase change, or change in phase is equal to 0. No phase change means 0 change. And for the light, for example, when it's going from water, oh, became water, and let's say if this is air, then it's going from higher to lower refractive index. So that means phase not gonna change. Okay. So this is for reflection, but for example, why light, part of the light gets reflected, for example, from the water surface, and same thing goes with the air as well, and part of them pass through the water. So that's why when we inside the water, for example, in the swimming pool, if we get inside the water and open our eyes, we can see underneath because there are light still there inside. Means light can transmit or refract to the water, right? So when things are refracting, for example, when wave is refracting, what happens? There is no change. So for example, the string example here, this is lighter string, which is equivalent to lower refractive index. And this is heavier. That means higher refractive index. Okay. So now what we see is the wave is coming here and hitting this boundary. So you have a thin string and let's say heavy string. And if you hold both sides, let's say one person holds one side, another person holds another side. And if one makes the wave by just swinging it, then this wave may come something like that. Once it hits the boundary, what happens? The reflected one basically changes the phase opposite because it's like going from higher to lower. So this acts like a fixed boundary. Okay. However, the one that is passing means refracted wave or transmitted wave. See, although it has a smaller amplitude, it has the same phase. See, it was swinging up here. Now I am swinging, it's swinging up there as well. Okay, so that means it's a representation of same phase. So here you see the speed is v, but here your speed is v prime. So the speed becomes different. Okay, so now if it goes from, let's say, higher n or higher density to lower, then what happens? See, still the same phase. So due to the transmission or refraction, they are not going to be phase change. No matter whether the light or the wave is going from higher refractive index to lower or lower to higher. Refraction, no phase change. Reflection, there is phase change, and we need to keep in mind, and that you can see here, there is phase change here for the reflected one. Okay, when it goes from lower to higher. So basically both information from the last slide and this new information, both of them are here. So that's why I put the title both reflection and refraction. We had just the reflection in the previous slide. Okay, so this is the main idea. Okay, so once we have that, then we can understand what's going on and what's going to happen. We can predict, And we can design thin film that can be useful. For example, they quote thin film on glasses. Uh, so that uses this idea and find the value of refractive index of the material so that the reflected wave basically destructively interfere. So that means it avoids the some sort of glare on the eye. Okay, it filters those light. So here I am showing you in the waveform. So you see here this wave is going something like this, and there is another wave. So here direction of motion I'm showing by putting this arrow here. Okay, so its arrow got kind of arrow is kind of hiding here. So this is moving this way. This is moving this way. So you can think of this as the same wave. Okay, part of same wave. One that gets reflected, another one that gets transmitted. Okay, so part of it gets transmitted, part of it gets reflected. So I'm drawing in two places to visualize it better, but both of these you can think of, entering from same place if you like. So here I am showing this wheelie thingy to remind ourselves that it is the wave we are talking about, not the ray. But drawing this all the time is not that, easy and very time consuming. So that's why most of the time we may just represent that by drawing the line. So when you see just line here in this chapter, you can imagine, okay, this is what happening, okay? So now what do we see here is that this gets reflected. So refractive index of air is 1 and refractive index of water is 1.3. So that means it's going to the higher refractive index. So it's reflecting from that boundary. So when it reflects from a boundary of higher refractive index, it changes the phase. So that's why this one and that one, they have 180-degree phase difference. Okay. So for example, here one is going this way, another one is going that way. They have opposite phase. Okay. So now one that transmits basically, yes, it changes direction a little bit, but I'm not showing all those details here, and arrives to this boundary. So now there is a glass underneath. So think about this. So there is a glass. If you have, that, let's say some sort of glass here, and then you have thin layer of water in the glass. So light ray arrives here. So this thickness, is really large that I'm showing here. What happens? The thin film means it happens in micrometer, but to visualize it, I'm making this a bit larger here, way larger than usual. So that's what happening. So that's what I am trying to represent. So when the transmitted or refracted light arrives to this boundary, now it encounters again a refractive index 1.5 means higher, right? So refractive index of water is 1.3, refractive index of glass is 1.5. So that means there is also a phase change. So this one also gets phase change in the reflection. And then when it refracts or gets to the air, it does not change the phase. So it goes through one phase change due to reflection. This goes through one phase change due to reflection. So due to the reflection only at the boundary, they have, they went through the same phase change. Means they have now same page as indicated by this trough is matching to trough. This crest is matching to the crest, something like that. So that's what I'm showing it here. But what happens is due to the path difference, there are going to be phase change. This wave traveled, came here and went back there. So that means this wave did not travel through this film of water at all. But this wave had to travel through that. It had to go down and it had to go up. So that means how much path difference is there. So that path difference is basically equal to this plus that. So if this angle is theta, this angle becomes theta. So in that case, what happens is this side length here becomes t sine theta because it's opposite of that angle there, and this t being the thickness of the uh, film. So what happens? We get t sine theta, and over here we get t sine theta. So that means total path difference, we can write 2t sine theta in this kind of situation. But these angles, often when we are looking at the light that's reflected, they are basically, they make very small angle. And because of that, we can say, okay, sine theta, uh, basically, uh, in that case, if they are making very small angle with the surface here, they are making almost 90 degree. So this sine 90 becomes kind of 1. So we can just write 2t. So it's like saying, okay, the difference in path is just going like a t here and coming back t, something like that. Okay. Okay, so we're going to be writing path difference as a 2t. Okay, in the thin film. So we can have phase change due to reflection, and we can have phase change due to path difference as well. So to make sure that we understood this, I have brought several questions here as a clicker. So, oh, I did not start clicker. So let me start the clicker. Simple yes, no questions here. Whether there are, there is phase change happening or not. Now, although they are wave, I'm just drawing the line to keep things simple and make my life easier as well. Okay, I'm opening the poll. So for this question, you have 1 minute and 30 seconds. So rays 1, it says, and you can see those rays are labeled something like that. Okay. So we're just talking about this one and that one for this question, nothing else for this particular question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So mostly A, and there is B as well. So did phase change between 1 and 2. So it has a refractive index 1. This has a refractive index 1.5. So this is acting like a hard boundary. So when wave reflects from hard boundary, it goes through 180-degree phase change. So it actually went through 180-degree phase change. So S is correct answer in this case. So now it may look like the same slide, only this thing changes here, okay? So everything else is same. So for example here, now we're talking about in between 1 and 3. Okay, so let me open the poll. And for this, you have just a minute. And 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what happened here. We have kind of A and B, yes and no. In this case, no is correct answer. So refracted. Also, we can say transmitted. So when wave gets refracted or transmitted, no phase change. Okay. So that's why B is correct answer in this case. Did I mark that? Yes. So now, again, so now between 3 and 4, we're talking about. Let me open the clicker question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Oh, we got half and half almost. So in this case, correct answer is no. Why is that? There is reflection. So this 4 is reflected part of this 3. So when there is reflection, there may be change in phase. But in this case, there is not because, see, the oil has a higher refractive index compared to water. Okay. So that means it's like saying, okay, it is like a loose boundary. Okay. Higher N and this is lower N. So when we have this kind of boundary, there is no phase change, and that's what we talked about a little early. Okay. Okay, so yes, it's easy to forget. So that's why I have all these exercise here. Hopefully it will make you remember. So now we're talking about 3 and 5. So 3 is here and 5 is here. Again, a minute. and 30 more seconds. Five more seconds. Five, four, three, two, one, and it stops. So in this case, refraction happening. So doesn't matter whether it's a higher or lower refractive index, as long as they are refracting or transmitting, there is no phase change. So no phase change. Oh, still looks like, a lot of you are still confused. I don't know why. Refraction, no phase change. Doesn't matter what kind of boundaries are those. Reflection, phase changes at the boundary going from lower to higher. Here it went from lower to higher here. Over here it went from higher to lower. 1.3 is lower, okay? So that's why there was no phase change. However, there was phase change here. Okay, so just this we need to keep in our head. So I think I have one last slide related to this question here. So now we're talking about 4 and 6. And you have a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly no, but there are still yes. So this is refraction. See, it's transmitting here from one medium to another medium. Whenever there is refraction or transmission, there is no phase change. Doesn't matter what kind of media there. Okay. So we're going to be using this idea. So you see this kind of color film, uh, colors in the soap bubble, or there could be, let's say, water sitting on a glass surface, and if you look from a particular angle you may see that colorful display. Usually it happens when there is oil spill, so you may see that color if you look carefully on that one as well. But soap bubbles, they are famous. So now, yeah, this is oil and water. So what we learned is that phase could change because of the reflection at boundary, and we learn when it changes. right? It changes when it goes from lower refractive index boundary to higher refractive index, and could change due to path difference as well. So before, when we used this condition, for example, double slit experiment, when we had light going something like that, we had this path difference, just like we have here for the thin film as well. It's like just, you know, two sides on the thin film, but in this one, just one side, okay? So when we did that, what happened was the phase change was only due to the path difference. But what is different now is that we can have phase change because of both of these. So that's why this constructive and destructive interference condition we used over there, to use that, we have to be a bit careful what's going on, without knowing that, just listening or reading constructive and destructive and using that condition may or may not be correct. Okay. So that's what we're going to be practicing, how we make sure that we are using the right condition. So this is just like we had before. So we have water, oil, and there is air, and the light is coming something like that, and it gets reflected. Okay. And there is 180-degree phase change. So this is just summary of what we just talked about. And there is no change in the transmission, and there is no change in the reflection because it is reflecting from low refractive index boundary. Okay. And there is no change for the transmitted one here as well. So now this one gets out. So this one never went through the phase change. Only phase change that happened was for this one here, reflected one, okay? So now when they come out, they have opposite phase, okay? They have opposite phase because this one did not change the phase, whatever it entered, that came out, but this one went through 180-degree phase change because of this reflection from this boundary. So the phase difference between them is 180-degree or pi radian. So this is just looking at the reflection only, okay, due to reflection only. But notice this ray had to travel more distance compared to this one over here. So it went through double. So assuming that, see here, thickness of these, so bubble, probably you may have noticed, they are very thin. Okay, so that means we can think, okay, this thickness is very close to, so this here is very close to this one over there. So the path difference in this case is 2t. Oh, looks like. So if there was no phase change between these two, then they would be, constructively interfering. But since there is phase change, they are destructively interfering. But what we see is, for example, color here means we are seeing there is constructive interference going on. Otherwise, it would be just dark. Okay. So what's happening is that means for this to constructively interfere with that, it has to go through exactly 180-degree phase change. So where does that happen? That happens because of this path difference. Okay, so we need to take account of that. So here is a question, and this is fairly long question. I mean, the solution gonna be fairly long, okay? But I have tried to explain everything here, and everything is written in the note as well. Almost everything is written right here on the slide as well. So here, just like what we had, there is oil and there is water. So oil is on top of water, and top of water there is, I mean top of oil there is air, of course, right? So we have this kind of situation, and thickness is given in terms of micrometer. So 1 micrometer is 10 to the power negative 6 meters. Okay. So for which wavelength in visible spectrum do you expect constructive interference for the reflection at normal incidence? Means light, they are basically, coming here, not making large angle, rather they are coming very close to the normal. That's what it means. Okay. So we want constructive interference condition. So now if we just look at, so now I have this drawn slightly differently. So there is air, so this wave is coming, and I am showing this wavy thingy to keep track of phase. Okay. So there is oil and there is water. Okay. And we know oil has the highest or largest refractive index, water has 1.3, and air has a refractive index of just 1, right? So it's going from lower refractive index to higher refractive index. So when it hits the boundary, what happens? Part of it's going to get reflected and part of it's going to go inside. So let's keep track of those page, just like we looked at the previous example. So the transmitted one, you see there was hump on the upside and there is hump on the upper side as well, because it went through the transmission, and transmitted wave, they don't change the phase. So that's why the hump on both of these are on the same direction. So this is incident and this is transmitted. Now the one that's reflected from the air oil boundary, this boundary, I'm showing that as a R1, and you can see here the hump got reversed, means the phase change is 180-degree. Okay. So the phase difference between these two, incident and reflected from this very first boundary, is 180-degree, that we can see just by looking at the these humps as well. So R1 has 180-degree phase shift because the refractive index of oil is bigger than refractive index of air. So that's what I'm showing, and that's why I'm drawing the way I'm drawing here. Okay. And the refracted one, what happens? It does not change. So now the reflected also does not change because the refractive index is now lower for the water compared to oil. So that's why you see that this is reflected ray from the second boundary. So this is reflected R1 and reflected R2. R2 is reflected from second boundary. So you see the hump is on the same side, means there is no phase change there. And when it comes out, it goes through the refraction, means there is no phase change as well. So we are looking at these two reflected rays. So when they arrive to our eyes, we may see constructive or destructive interference. So for this problem, we want them to constructively interfere. So that, see, the question is saying, okay, we want to, filter out the wavelength they go through, only the one that goes through the constructive interference. So by just looking for the, reflection only, they have 180-degree phase change. Okay. and reflection only. See, two things can change phase. And here, so far, we looked at the situation when, what happened to the phase due to reflection only. Okay? We haven't looked at the phase change due to this thickness. So here, 100 out 180-degree phase shift means they're going to go through destructive interference due to reflection only. So now if we want constructive, then we want this to be coming out something like this, the same page with R1. We want constructive. So we want this to be reversed phase. So what can change the or reverse the phase? By controlling the thickness of this, we can reverse the phase. So reversing phase is like making it destructively interfere. But here that destructive interference becomes constructive. Why? Because there is already a phase reversal because of the reflection. So I'm writing those things here. So now let's move to another slide here. So I am just now focusing on these two reflected ones. Okay. So now see the R2 is missing here. I'm talking about R3. Now I'm making R3 at the same phase. And how can I do that? By controlling the thickness so that it inverts the phase. Okay. And that's what I'm doing that. Okay. I'm writing all those. So see, although we are looking for constructive interference and we learn that constructive interference occurs when we have m times lambda, but we are writing this equation. Why? For this to make constructive interference, we have to flip the page. And the flip changes when, the page changes or page flips only when we have this destructive condition. So there was one destructive condition coming from the path difference. Sorry, not the path difference, but the reflection. And now another destructive condition. So two destructive condition kind of makes a constructive because the phase now becomes same. So they are in same phase. Okay, so now you see the condition we used was this lambda, but here I'm writing this wavelength in a while. So what happens? We learn that wavelength of the light changes, right? When we're talking about refraction, we learn that wavelength of light changes when it goes from one refractive index material to another refractive index material. So that's what we learn. So that means the oil has a different refractive index means it has a different refractive index than air. So the usually when we write this equation, we are writing this for air, right? When we had two slit experiment, what happened? It just passed through two opening and there was just the air everywhere and near the screen, all the air. So everything was happening on the air, okay? So that's why we had this wavelength. But here what happened is this path difference took place inside the oil. So because of that, when we write this formula, we need to write the wavelength of the oil. Okay, so two things. One, how the wavelength changed here. We need to take account of that. Another thing why, although we are saying constructive interference, why we are writing the condition for destructive interference. And actually what this thickness is doing is basically flipping the page, and that is the condition for destructive interference. That's what we want it to do, neglecting this one for the moment. And when it flips, then it brings them to the same page, and because of that, what happens? They constructively interfere. So that's why this equation is like this. So to understand that, we had to go through this long discussion, okay? Okay, so now we have this condition. So thickness is fixed. So now what happens is this m gonna give us the different values of m gonna give us different wavelength. Okay, so that's what we want to figure that out. So I just copied that equation. So we don't know the wavelength in oil. That's what I'm saying. So how do we figure that out? So for that we can use the definition of refractive index, right? So C and V, we can write them in terms of frequency and wavelength, but this is for air and this is for oil. So that's what I am doing here. So refractive index is this, and for the oil, the speed gonna be speed on the oil, and for the air, the speed gonna be speed on the air. And speed in the vacuum and air, they are about the same. So refractive index in air is just 1. But over here, let's get rid of C, which is common. So to get rid of that, we can divide 1 by another one. When we do that, this C cancels, leaving us just the speed. Now we can write speed in terms of frequency and wavelength. And what happens is the frequency does not change when it goes from one refractive index to another refractive index material. Only the wavelength changes. So that's why the frequency cancels. So the ratio of the refractive indexes is equal to the ratio of the corresponding wavelengths. But you see here, there is oil on the top, but air on the top over there. So they are inversely related. Okay. Higher the refractive index, lower the speed, or smaller the wavelength. So that's what it is saying. So now I can write refractive index, sorry, the wavelength of the light or the wave on the oil in terms of refracted wavelength in the air. See, wavelength in the air. So if you, for example, let's say look for what's the wavelength of the red light, the least you see or the number you see is for the wavelength of that light on the air. So that is easily available, but this one is, we need to figure that out. And the formula to figure that out is this. Since the refractive index in air is very close to 1, we can simply write this something like this. So when I was writing the note, I was kind of, a bit tired. So I did not went through this, and I simply wrote that lambda in any medium, I wrote this formula, let's say, lambda in any medium is lambda in air divided by the refractive index of that medium. I think over there we simply wrote lambda n is lambda divided by n. So lambda in a medium, that's what this n here represents, refractive index of a medium, is equal to lambda on air divided by the refractive index of this medium. So in this case, the refractive index is going to be refractive index of the oil because that's where we want that wavelength. So that's where the flip, changing of the phase is happening, or that's what we want. Okay, so this was just, writing this formula. So now we can go back here and replace this lambda oil by lambda air divided by the refractive index of medium. Okay. Yeah, in the short, it's written right here. So that's what I'm doing. So it was lambda oil over here. So now I'm writing that as a lambda air over oil. So now we want to figure out the wavelength. So the question is asking us what wavelength that you see the constructive interference. So this is condition for constructive interference for this thickness of the oil. So what wavelength in the air, gives us that. So this N oil is fixed, T is fixed for our setup. So only thing that's changing is M. So we want to put value of M 0, 1, 2, and so on, and calculate the value of wavelength. Okay, so that's what I'm doing. For M is equal to 0, when we put 0, what happens? This fraction of fraction. So for M is equal to 0, this lambda here becomes 2 times T times refractive index of oil, and then 1 over 2 means this fraction of fraction, it goes up and it multiplies that. Okay, so when you plug in this thickness, so here I'm just leaving that in micrometer because thickness is given in micrometer in this problem. Okay, and refractive index of the oil. So when we do that, we get this number. And now we repeat that. And when M is equal to 1, then what happens to the wavelength? So like before, this is still there, but this is now 1. So 1 plus half is 3 half. So what do we get? 4T N oil divided by 3. And that's what gives us this number, and so on. Okay. So looking at this, what happens is this has a shorter wavelength. So that means it's not visible. So only light that is visible to our eye in this case is just that 0.48 micrometer or 480 nanometer. So which color is this? How do we figure that out? We need to search, okay? Which color has this wavelength? Okay. So what happens is the visible goes from around 400 to 700 nanometer. So if you can remember, that's going to be handy, but you can, for example, look at the book or search in the internet. And so this being very close to here, 480, very close to there. So it looks like it's going to be blue, some shade of blue. Okay. So what you're going to see on the film based on this question is that it's going to look bluish rather than red. So let's see, we had that, oh, it's way back, but I want to see that. So you see here, there are bluish color, there are red color, reddish color, purple color. So there are these different colors because the thickness is different at different part of that soap bubble. It does not have uniform thickness. Okay, so because of that, at different part you see this different colors. Okay, now I have to go back all the way there. So these waves are not visible, although if they were going there and coming back, they would be constructively interfering, but those are our eyes cannot detect all these, only this can be detected. So I understand this was long problem or long solution, I should say, but it uses all the idea or the knowledge that's needed for this chapter, right? So I see this is already 3:01. So let's take a break. If you have any question, you can ask me after break. Okay. I'll see you in 5 minutes. Welcome back, folks. So before break, we did this problem that had relatively long solution because I went through great length of explanation. If you have any question, please feel free to ask. Okay, looks like there is no question. So let's move on. So you see here, if you put two glass slides, these slides are usually, if you have used microscope, they put samples on that slides and slide underneath this objective lens, right? So it is a picture of that, okay? So you see here, there are these interference pattern. Some of them are, they have like one color, another one has another color, and they have this different shape. So why? Because the thickness of the air trapped inside these glasses, they are, they have different, the thickness is different. So for example, if we were to press that glass, something like that, then this pattern changes, as you can see, because the thickness changes. So it gets pressed, so thickness of the air film inside changes. And because of that, what happens? You see this change. Now, the application, for example, in real life, let's talk about that, of this thin film interference. So there are several applications, but one commonly used application is coating on the glasses. Okay, so you see here, without coating, you see something like this. That's not so good, right? But over here you can see the clear view if it has a coating. So how does it work, right? So let's follow. So there is a glass and there is coating on the glass, okay? And there is air. So let's suppose light is entering. So here we are looking at the light reflected and getting to our eyes. So that means our eye is on this side here, okay? Our eye is on this side. So that means we are looking from the side of the eye, okay? So now what happens? The light that's reflecting, so light from the object comes to our eye, enters to the eye, and then what happens? That's what makes the image, right? So in this case, some light, maybe, they get reflected and then that becomes unwanted, and we want to get rid of that. And that's where this coating comes in, play. So for example, let's suppose this red light wave is coming and hits the coating. So at the boundary, two things happens. One, it continues. So there is transmission And yes, I spent quite a length of time here drawing this to match the phase as well. So here you see they have still same phase, but the amplitude becomes smaller when they enter through the coating, right? And so this is transmission or refraction. So that means there is no phase change. So that's why it was coming with the hump on the top. Now it is also going hump on the top. So that's what I'm drawing as the same phase. Okay. So they have same phase. And the one that gets reflected from here, I'm drawing that as a red wave over there. Okay. So it's got reflected from the coating right there and goes toward the eye. And as you can see, they have opposite phase. It has a, you know, peak over there. This one has a valley lined up with that. Okay. So it went through 180-degree phase change. So now we don't want this light. So we want only the light that came from the object to enter into our eyes. We don't want this light that's reflected from this glass to enter to our eyes. When that happens, that's when we see this kind of glare. Okay. So we want to cancel this. So that means we want this to be destructively interfering with the light that comes from reflected from this glass. So if there was no coating, there wouldn't be another layer of that. Okay. Rather, what would happen is that there would be reflection from the glass only, just like you see. There is no care coating. So the reflected light just enters to our eyes. That means we see that glare. But when there is a coating and suitable width of or the thickness of the coating, then what happens is the light get there transmitted, that gets reflected here, okay, and it's coming going through the one phase change as well. So it's arriving something like this. So often these materials that used they have higher refractive index than the air, but lower refractive index than the glass. Okay, so because of that, what happens? This blue light that was transmitted light, it goes through phase change, 180-degree here. Okay, so this one went through the phase change right here, red at this boundary. Blue went through the transmitted one. I'm showing that as a blue that went through the uh, phase change at this glass boundary. And now it does not change phase when it's coming out. So that means they have now same phase. So that means if we don't adjust the coating to get rid of that, to invert the phase, then they would be constructively interfering and would be even worse. But if we adjust the thickness, then what's going to happen? Then we can invert the phase of this one right here. When it comes down here and gets out, when it travels this path, during this time, we can make it invert the phase one more time due to reflection and due to the path difference. So we can make it double phase change. And when double phase changes, what happens? Rather than lining up here, now that would be basically in the opposite phase compared to this one over here, and this is going to be canceling. And that's why you see this clear vision like that. So for that to happen, again, you have to invert the phase, means you have to use this condition. 2t is m plus half and lambda, okay? And this lambda has to be for the coating. So that means we need to know the refractive index of coating. So this can be written as m plus half lambda air divided by refractive index of coating. Okay, so that's how we need to write this equation, because we have to invert the phase. Okay, so that's why this equation becomes this. So anyway, so that's how the reflection, or the interference, I should say, interference in the boundary can be useful sometimes if we can adjust them properly, control them, like using thin film here coating, or could be bad, okay, even more bad. And there is another thing that may happen because of the reflection at the boundary of two surfaces. That's what we call polarization. So polarization can happen because of the transmission, or could be because of the reflection as well. So we talked about polarization and what polarization is briefly when we talked about waves. Okay. But here I'm just looking at one special situation. The light or wave may get polarized when it reflects from a boundary. So this animation I found, so this I did not make myself. So I just steal from somewhere and I forgot to write where I stole from. So here you see this light is, oscillating in all directions. So that's what the ordinary light looks like. And it arrives to this surface in this animation you see here. And then what happens is the light that is reflected has orientation in just one direction. When that's the case, we say, okay, it is polarized light. It is called polarized. The one that's transmitted, it is still not polarized, but it is partially polarized. But over here, it is polarized. So that's why when you are, let's say, there is early in the morning, you are somewhere in the lake or some sort of reservoir standing, and then there is water, being reflected, and it is arriving to your eye, reflected light from that boundary of the water and air arriving to that. So you see a lot of glare for most of the places. But if you duck down a little bit or change the angle of your head, in some cases, you may avoid that glare. So you can still see the water, means the light is still coming from the water and entering to your eyes, but only the polarized one are entering at that particular situation, okay? So light, so in short, wave can be polarized just by reflection. So we can use polarizing devices, we can use polarizing glasses and so on. That makes light polarized, but simply reflection from the surface can also make light polarized. But it has, for that to happen, it has to satisfy certain condition. So before we talk about that condition, I have a question. So here I'm showing you, the light. The dot means LiDAR. So that detail is not necessary to answer this question. It is just purely a geometry question. Okay. So, but here the light is oscillating in this direction. It's like saying, okay, that one. So this is another way to show that kind of oscillation. And the one that is dot is perpendicular to that. Okay. So this is coming here, hitting the interface, and this is normal to the surface. So this angle of incidence, let's say, is equal to angle of reflection, and this is transmission, and these angles are related. We learn about reflection and refraction, right? So these two angles are same, but this is not same as those. Here, what I'm asking you is, what is the value of this angle and that angle? And you see this shown here, this means it is 90 degree. So often the angle, they are denoted by, you know, shown something like this with an arc. But if we have a 90-degree or perpendicular, you may draw something like this. So it shows this is 90-degree. Now, what is the sum of this angle and that angle? Little bit geometry here, folks. So I'm opening the poll, and you have a minute and 30 seconds. 30 more seconds. 30 more seconds. Oh, 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see over here what we got here. So mostly B, that is 90-degree, and that is correct because this whole line here, when we have that, that is 180-degree, right? This versus that, we know that is 180-degree. It's like this versus that, that is 180-degree. Now, since the angle between these two here is 90-degree, so that means this is going to be 180 minus 90, right? This sum going to be 180 minus 90. Or another way to look at is theta r plus 90 plus theta t is, the whole thing is 180-degree, means theta r plus theta t is 180 minus 90, means it is 90-degree. Okay? So it turns out that light gets polarized when the angle between these two is 90-degree. Angle between reflected and refracted rays of light, when the angle between reflected and refracted rays are 90-degree, when this angle is 90-degree, in that case, what happens? The reflected light becomes polarized. So that's what the experiment shows, okay? So we're going to be using that knowledge here to figure out what angle, at what angle, when it enters to this medium, we're going to get this polarized reflected light. So that's what we're going to be learning in the next slide. So same diagram you see, this side has a refractive index N1, which is smaller than refractive index N2, okay? You can see that here. So now, let's focus on this one. This is refraction, right? So this angle and that one. So that angle, although, you know, often we write that as an angle of incidence, theta I, but in this case, we are looking at this particular situation when this becomes polarized. When this condition is satisfied, this angle of incidence is called Brewster's angle, and that's why, you know, it's written as a theta B here. Okay. So now, using the Snell's law between this incident and refracted ray, see here on this side, the refractive index is N1. On this side, refractive index is N2. So that's why N1 times sine theta B is equal to N2 times sine theta T. So that is the Snell's law. We learn Snell's law something like this. So refractive index and the angle has to be from the same side while using this equation. And this equation, Snell's law, I'm using that for this particular setup. So now we want to figure out theta b. Okay. So to figure that out, it's if we use this knowledge that theta t and theta r, sum of them has to be 90°, then we can replace this theta t by theta 90 minus theta r. Okay. And we know theta r, which is this here, angle of reflection, and this angle of incidence, they are equal because of we know that they are equal, and we learned that when we talked about reflection. So they follow the reflection law. Okay. So that means I can replace this theta r by theta b. So that's what I'm doing. So that way, what happens if I can replace this theta t by this 90 minus theta b in this equation, only angle we're going to have is just the theta b. So once I have sine theta t replaced by 90 minus theta b, now this equation we have, and this equation has just the theta b as the angle. It is in two different places. That's a different story. But one equation, one unknown means we can solve for it. Okay. So that's why the reason we use this geometry here to write this transmitted angle in terms of, excuse me, this incident angle or angle of incidence. Okay. So let's do that. Oh, what happened? Big jump there. So this is sine 90 minus theta. So the right hand side becomes n2 sine 90 minus theta b. And sine 90 minus theta, if you took trig sometimes somewhere, then that becomes cosine. But here I can show you by just drawing this wave. So sine starts from 0, right? So if I'm plotting sine function, this is how it looks like. If you move this by 90°, either one way or the other, what happens? So if you move 90° means quarter cycle, then now it becomes cosine. You see that? So that's why the sine 90 plus theta or sine 90 minus theta, in both cases, what happens is it becomes cosine, because 90 minus theta means here, so that is, let's say it arrives here. Okay, so that becomes like negative cosine theta, and negative cosine theta and cosine minus theta, they are basically, that becomes, let's say, cosine negative theta, and cosine negative theta is also cosine theta. So that's why whether it is positive or negative, it is just cosine we're talking about. Okay, so it's a trig identity or formula from trigonometry, or if you can visualize this wave, you can see that on your own. When you shift sine or cosine by 90°, when you shift sine by 90°, it becomes cosine. When you shift cosine by 90°, it becomes sine. Cosine can become sine, or sine can become cosine when we shift the angle by 90°, and that's what we are doing. So that means it becomes n2 cosine theta b. So we have n1 sine theta b on this side and cosine theta b on that side. So if I bring this on this side, it becomes sine theta b over cosine theta b. and that is equal to n2 over n1. And now this is tangent theta b. That way the angle is just in one place. See, little trig help us to solve this equation. See, to solve an equation, we have to have unknown only in one place, and that's what we did here. Okay, so now to solve for theta b, we take the arctangent or inverse tangent. So now let's look at one example here. Although I did not write that on the slide, I did not bring, another slide. We can look at here. So for example, let's suppose you are standing near the lake or by the lake where there is air. So N1 is 1 for the air. And there is water. Let's say N2 is 1.3. And this is for, let's say, water. So usually we may see it's written as a 1.33. Okay. So that is N2. So now, if you are standing here and your eyes are there, let's say you are standing somewhere here and your eye, you are getting that light and you are seeing that there is a glare on the light. You want to avoid that. So where you should be putting your head and what angle so that you don't get that glare, just the polarized light coming to your eyes. So to calculate that angle, we can use this formula we just talked about. Okay. So in this particular case, for the boundary of air and water, the angle gonna be inverse tangent of N2 means here water, which is 1.33, and divide that by 1, so it does not matter. So basically it is arctangent 1.33. So I know, 1045 degree is 1. This is bigger than 45 degree. So I guess it's going to be somewhere between 45 and 60, I think, somewhere. And if you have calculator handy, can you calculate that and type that on the chat, please? So I'm expecting this number to be bigger than 45 degree. And I see there is a direct message that came that says 53.1. That sounds reasonable, but if someone else did that and verified that, then would be nice. So yes, so looks like 53. So you need to stand. So if you are standing on the water, I mean on the side of the lake, not on the water, and if you have glare, then you want to line up your eyes at around 53 degree to avoid it. Okay, so that means what has to happen is, remember this angle we talking about, which is same as that in this case. So you can avoid only when, you know, the sun is at a particular angle. So if it is at different angles, then you may not be able to avoid it. Okay. Okay. And it says that's what Google said. Okay. Google is, of course, better than your teacher. So, yes. So that's that. So that's all I have for this chapter. And next chapter, we're going to be talking about relativity, Einstein's theory of relativity. Okay. And that is also very interesting, bit challenging to our mind. It may challenge our mind, but kind of interesting. Okay. So that's what we're going to be doing next class. So today I will just, leave it here. Please feel free to stop by and ask me question if you have question.